Hi class, welcome back to Multivariate Calculus. And in this lecture, we are going to learn how to determine whether or not a local min or max critical point is in fact a global min or max. So to begin, let's start with a warm-up. Let's see how much you remember from last lecture. So to warm up, find the critical points for the following. So first, find the critical points for f of x is equal to xy minus x squared minus y squared minus 2x minus 2y plus 4, and b for f of x is equal to 1 over x plus 1 over y plus xy. So pause the video here, give it a try, and when you're ready to see the solution, hit play. All right, so let's go through the solution here. Okay, so for this first one, in order to find the critical points, we first need to find the first order partial derivatives. So we need to find the gradient. So with respect to x, 1 second. So with respect to x, the first order partial derivative is going to be y minus 2x minus 2y. Oops, just kidding. That y squared is treated as a constant because we're taking a partial derivative, minus 2. Okay, and then the 2y plus 4, that's treated as a constant. So then for our first order partial with respect to y, we are going to have x minus 2y minus 2. Okay, so now what we need to do is we need to take one of these and set it equal to 0 to see if we can find some roots. So let's begin. So if we have 0 is equal to y minus 2x minus 2, we end up with y is equal to 2x plus 2. All right, so over here, let's do the same thing. 0 is equal to x minus 2y minus 2. So in order to find the roots here, in order to find the critical points, what we need to do is we know that y is equal to 2x plus 2 from our partial with respect to x. So we need to take that and plug that equality in for y. And so then we can rearrange and solve for x. So 0 is equal to x minus 2 times x plus 2 minus 2. So this gives us 0 is equal to x minus 4x minus 6. Okay, and so then we end up with 3x is equal to minus 6, which tells us that x is equal to minus 2. All right, and so quickly, I'm going to go and figure out what y needs to be when x is minus 2. So going over here now, we have y is equal to 2 times minus 2 plus 2, which gives us minus 4 plus 2, which is also minus 2. So our critical point is going to be minus 2 and minus 2. Okay, so that's our first one. So now let's find the critical points for our second part. So for our second part, once again, we need to start with the gradient. So we're going to have partial with respect to x is going to be minus 1 over x squared plus y. And our partial with respect to y is going to be minus 1 over y squared plus x. So if we set the first order partial with respect to x to 0, we get 1, or y is equal to 1 over x squared. And over here we get x is equal to 1 over y squared. Okay, and so what do you notice? Well, when is the only time you can have this work out? When is x squared going to be equal to x, for example, or y squared going to be equal to y? So the only solution here is that x is going to be equal to y is going to be equal to 1. Okay, so that tells us that our critical point is 1, 1. All right. So far, so good. Hopefully, let's move on to our new topic, the global extrema. So now that we have these critical points, how do we figure out if they're global maxes or global mins? So what we're going to do is we are going to work from our functions from the warm-up and figure out if our critical point from the warm-up is a global max or global min now. So for our first one right here, our critical point was minus 2 and minus 2. All right. Now, we had let me just write out our first order partials, our gradient. So we have y minus 2x minus 2. And with respect to y, we have x minus 2y plus 4. Okay, so now let's take our second order partials. So with respect to x, we're going to have minus 2. And with respect to y, we're also going to have minus 2. And then looking at our mixed partial, let's look here. So we are going to have, let's see, so with respect, f of x with respect to y is going to be 1. Pausing for 1 second. All right, let's keep going. So our mixed second order partial right here, so with f sub x with respect to y is just going to be 1. Okay, so now we need to compute d to figure out if we have min, max, or saddle. So d is going to be fxx times fyy minus our mixed squared. So just a little note on this d. Once again, I mentioned before that this was the determinant, so let's just look at where this actually comes from. So d is going to be the determinant of our matrix of partials, of second order partials. So f x x, f x y, f yx, and fy. Okay, so that's where this piece comes from. Okay, let's keep going. So for D, we end up with minus 2 times minus 2 minus 1 squared is 1. And so we end up with 4 minus 1, which is 3, which is greater than 0, which means we have a min or max. All right, and so now we can look at our fxx or our fyy, and we notice that they are negative, and negative means concave down. So we're concave down, and so that means we have a max. And so now we got to figure out if this maximum is a local or a global maximum. So the way to do that is let's first compute the value at our critical point, which we know is some kind of max. Okay, and so plugging in minus 2 and minus 2 into our function up above is going to give us 8. And so now let's try to figure out what some output of points around minus 2 and minus 2 are, just to see what we think, some trial and error. So if we plugged in 0, 0, we end up with 4. If we plugged in minus 3 and minus 3, we end up with 7. Okay, let's try another few combos. Let's try, say, minus 3 and 0. We end up with minus 2. Or if we tried, say, 0 and minus 3, we get minus 2. So I'm trying for points around our critical point in different quadrants. Okay, smaller than, larger than, that kind of thing. And it's suggesting to us that maybe, in fact, this is a global maximum. And so let's just take a look at GeoGebra to see what this plot looks like. So looking here, we have our function, and oh, here we go. All right, so this point A is clearly a global maximum in this case. And just looking at the function, you should have that sense right here. Okay, let's try another. Okay, so let's try part B. And feel free to pause this at any time and try it on your own first, and then hit play to see the solution. One of the great things about online recordings. So let me just write down once again our first order partials. So with respect to x, we have minus 1 over x squared plus y. And our partial with respect to y was going to be minus 1 over y squared plus x. Okay, now we have to take the second order. So with respect to x, we end up with 2 over x cubed. And with respect to y, we end up with 2 over y cubed. And remember our trick. So it's always easier, for example, when dealing with the power in the denominator to say, okay, this is the same as minus 1x to the minus 2. Okay, so you bring the minus 2 out front, minus times a minus is a positive, and you subtract 1, so we end up with minus 2x to the minus 3, right? Or sorry, positive minus a minus, so positive 2x to the minus 3. And let's do our mixed partial here, and this is just going to be 1. Okay, because right here, taking the partial derivative of f sub x with respect to y, the derivative of y is 1. Okay, so let's keep going. So now let's compute d at our critical point, which was 1 and 1. I'll just write our critical point up here again, 1 and 1. All right, and so this is going to be 2 times 2. Okay, so plugging in 1 for 2 over x cubed and 1 for 2 over y cubed. So that's 2 times 2 minus 1 squared, which is just 1. And this is going to give us, once again, 3, which is greater than 0, which tells us we have a local min or max. Okay, so now let's see if we think this is a global min or max. Actually, we have to figure out if it's a min or a max. So let's look at the concavity. Okay, so we have positive values here. So positive value tells us that we're concave up. Which means we have a minimum. Okay, so let's try to plug in some values. So first, let's evaluate our function at our critical point. Okay, so it's going to be 1 plus 1 plus 1, which is 3. Plugging into this up above. And let's try another one. Let's try minus 1 and minus 1. See what that looks like. Okay, and we find that this comes out to minus 1. And 3 is, of course, greater than minus 1. So we do not have a global minimum. We have a local min, okay? So our answer here is no, we do not have a global extreme. Now, to verify, let us look at the plot in GeoGebra. All right, so you can see here that our point A, our critical point, is in fact a local minimum here. It is not a global minimum for our function. Okay. Let's try another exercise. So for this one, we are going to apply our method for determining extrema to finding the least squares line that passes through the points 1, 2, 2, 4, and 4, 7. So what you're doing when you're performing least squares regression is you're trying to minimize the area if you were, okay, so let's look for 1 sec. So if we looked at this point right here, it's some distance in the y away from our best fit line, and it's some distance to the x, from the x for our best fit line. And so if we use those distances in the y and x direction, and we calculated the area of a square for its distance away. Okay, so points that are directly on our best fit line are going to have no square, right? They're going to be 0 away in the y direction and 0 away in the x direction. So that would be 0 area away. So we want to minimize the total area for our points away from the best fit line. Okay, so we're looking for a minimum here. So let's begin. Okay. Now, zooming in once again. So if we have a line here, a best fit line, I'm going to make it red. And we have a point on the line. And let me put some other point below it. Okay, so this point on the line is going to be in reference to some x coordinate. I'm going to say it's x1. And it's going to be the equation of our best fit line, which we all remember. To get the equation for a linear equation is y equals mx plus b. So to determine the y value, it's going to be m times our x coordinate plus b. Okay, so that would be if you're on the line. That's for the best fit line. So our actual coordinate is going to be x1 and some y1. So our goal is to minimize the difference between these two. Okay, so let's keep going with our example. So we're going to generate a function, okay, and we have 3 points. So we have, let's say, x1, y1, x2, y2, and x3, y3 in general. So our equation here, our function, it's going to be a function that we're generating of slope, m, and b, our y-intercept. Okay, so this is going to be m x1 plus b minus y1 squared. Okay, so the square area. So we're taking the difference between the point, if it were on our best fit line, and the given actual point. So this would be our data, and this would be our linear model. Okay, observation, linear model. Okay, and so we're going to do this for each one of our given points, each one of our observations. First observation, second observation, third observation. So let me add on here, plus x2 plus b minus y2 squared plus parenthesis there we go, x sub 3 plus b minus y3 squared. So our goal is to minimize this. So now, for us, let's plug in our values. So f of m and b is going to be equal to m. Okay, and x1 is just going to be 1, so 1m. Okay, plus b minus our y1, which is 2, squared. Okay, plus x2 is 2, so it's going to be 2m plus b minus y2, which is 4, squared, plus our last one is going to be, let's see, x3 is 4 plus b, 4m plus b, and our y is 7, and we're going to square that. Okay, so now we have to minimize this function. So we have to get the gradient to find the critical points first. So in order to do that, we have to take the partial derivative of our function with respect to m, and then we have to take the partial derivative of our function with respect to b. So let me use a different color for this. F sub m is going to be 2. Okay, so we're just taking the partial with respect to m here. So we have the power of 2 that we're bringing out front. And inside our parentheses remain the same. So that's going to be m plus b minus 2. And we drop the power down 1, so it's to the first power. Okay. Plus, so power of 2, bring it in front, 2 times 2m plus b to the minus 4. However, we're taking the derivative with respect to m, and so you see there's a coefficient of 2 in front of this m, so that also needs to be multiplied. So the whole inside needs to be multiplied by 2, so the outside needs to be multiplied by 2. So we end up with 4 times 2m plus b minus 4. Okay, and then last one, we end up with 8 times 4m plus b minus 7. Okay, and then we can take our partial with respect to b, and that is going to give us 2m plus b minus 2 plus 2 times 2m plus b minus 4 plus 2 times 4m plus b minus 7. Okay, so now we got to go through and clean all of this up and simplify. So I am going to start a new sheet in order to do that. Okay, so let's start a new sheet here. And this is still example exercise 21.2. Okay. So, working on this, FM is going to clean up and simplify. Well, let's expand out first. So we have 2m plus 2b minus 4 plus 8m plus 4b minus 16 plus 32m plus 8b minus 56. Okay, so this is going to be 42m plus 14b minus 76. And for our partial with respect to b, that simplifies, well, let's expand out, and we get 2m plus 2b minus 4 plus 4m plus 2b minus 8 plus 8m plus 2b minus 14. And if we simplify, we get 14m plus 6b minus 26. Whew! All right, we're part of the way there. All right, let's keep going. So what we need to do is we need to find the critical points. And so the critical points occur when our first order partials are 0. Okay. And so setting FM equal to 0, for example. Actually, let's start with setting FB equal to 0. So we end up with 0 is equal to 14m plus 6b minus 26. And so from there we get m is equal to 26 minus 6b over 14, which is the same as 13 minus 3b over 7. Okay? And so then what we need to do is we need to set fm equal to 0 and plug in m equals 13 minus 3b over 7 for m. Okay, so I'm going to do that on this next page. So using fm is equal to 0 is equal to 42m plus 14b minus 76. And remember, for m, we found that it was going to be equal to 13 minus 3b over 7. Okay, let's keep going. So now we have 0 is equal to 42 times our m, which is 13 minus 3b over 7, plus 14b minus 76. Okay, and this is going to give us 78 minus 18b minus 76 plus 14b. Okay, and so we end up with 4b is equal to 2, and so b is going to be 1/2. Okay, so we have our y-intercept after all of that. So now we just got to figure out what our slope is, m. So to get m, we have plug back in. So we have 13 minus 3 times 1/2 over 7. And that is going to be 23 over 14. Okay, so our critical point is 23 over 14 and 1/2. And next step, we're going to have to do the d-test on it to figure out if, in fact, it is a local min, local max, saddle point, what have you. So let me open up a new page. Okay, we're almost there, I promise. So we need to take our second order partial derivatives. So let me just write the first order down once again. Fm is going to be 42m plus 14b minus 76. F sub b is going to be 14m plus 6b minus 26. So second order partial with respect to m is going to be 42. And second order with respect to b is going to be 6. And the mixed is going to be 14. Okay, so then we have to calculate D at our critical point, which was 23 over 14 and a half. Okay, and so let's plug in, and we end up with 42 times 6 minus 14, and this is going to be equal to 238, which is greater than 0. And here, the FMM is positive, so we are concave up, so we have a local min. So there's our local min. So we're minimizing it, and you can go through and check out some different points, but this is in fact going to be our minimum. And so our final answer is the equation is going to be y is equal to mx, so 23 over 14x plus 1/2, which is approximately 1.643 x plus 0.5. There you have it. And you can always try to plot out our function, that was a function of m and b in GeoGebra, and check out the critical point to verify, once again, whether it's that it is actually a global minimum. All right, now we're going to do another one. And for this one, I would like you to definitely try it out on your own. So it's going to be find the dimensions giving the minimum surface area for an open box with a volume of 32 square centimeters. So pause the video, give it a try, and then resume to see the solution. The solution. So we want to minimize the surface area for an open box of volume 32. Oh no, I just now noticed that it should be, of course, obviously, 32 cubic centimeters. So hopefully you guys noticed that. There we go. Let's keep going. So volume of 32 cubic centimeters. So surface area, I'm just going to call it S. It's going to be length times width, right? Because we have an open box. Okay, so we only have 5 sides rather than 6. It's going to be length times width plus 2L times H plus 2W times H. Okay, and so what we need to do is, what else do we know? We know that it has a volume, so of 32 cubic centimeters. And how do we find volume? Well, volume, whether it's an open box or a closed box, is going to be the same formula, and it's going to be length times width times height. And it doesn't really matter which one you solve for, but we can say is we want to reduce the number of variables that we have. So let's just say here that H is equal to 32 over LW. So this way, we're trying to minimize a function of 2 variables rather than 3 variables. Okay, so if we plug in 32 over LW, we have S is equal to length times width plus 64, so 2 times 32 is 64, and L times H, so H was our 32 over LW, the L over L cancels, And so we have 64 over W plus 64 over L. All right, so now let's take the partial derivative with respect to L. So we end up with W minus 64 over L squared. And similarly, the partial with respect to W is going to be L minus 64 over W squared. Next up, we have to figure out, we have to find the critical point, right? So where our gradient, so each of the partials is 0. Okay, so when SL is 0, okay, so that gives us W is equal to 64 over L squared. Okay, and so then if we plug in 64 over L squared for W in our partial with respect to W and set that equal to 0, we end up with 0 is equal to L minus 64 L to the 4th over 64 squared. So this is going to be the same as L minus 64 L to the 4th. And that's not 642, that's 64 squared. It's a little hard to tell there. And so then we can, let's pull out an L. 0 is equal to L times 1 minus 64 L cubed. Okay, so that tells us that L cubed is equal to 64. So L is equal to 4. All right. Because the thing is, we can rule out here L is equal to 0. Because if any dimension of the box is 0, the total volume would be 0. Okay, so we know that is not even an avenue we want to travel down. So now we have L is equal to 4. So let's add a page. And this is still exercise 21.3. Okay, so let's keep going. So L is 4. And so, all right, so now that we know L, we can go ahead and figure out W and H. So W is going to be equal to, if you recall, 64 over L squared, which is going to give us 64 over 16. So we get 4. So length and width are both equal to 4. And then we can go through and figure out that H is going to be equal to 32 over LW, which is going to be 32 over 16, which is going to be 2. All right, so we have 4, 4, and 2 in this case for our critical point, for our dimensions. Okay, so now we have to keep going and use our test. So let's just write down again. SL, so the partial with respect to L was W minus 64 over L squared. And S with respect to W was going to be L minus 64 over W squared. So then we can take the second order partials. So with respect, the second order with respect to L is just going to be 128 over L cubed. Second order with respect to W is going to be 128 over W cubed. And the mixed second order partial is just going to be 1. So then we compute D at our L and W of 4 and 4. And that is going to be 4, ultimately 4 minus 1, which is going to be 3, which is going to be greater than 0, of course. And SLL is going to be positive. So we are concave up. So we have a local min, or this is our minimum. So we have the dimensions, and if you want to be very clear with the dimensions, we have length equals width equals 4 centimeters. It's very important to include units, and height is equal to 2 centimeters. So that one is done. I know there's a lot of steps in these problems. All right. So last one for the day, for the lecture. So exercise 21.4, we're going to design a rectangular milk carton box which holds 512 cubic centimeters of milk. The sides cost 1 cent per square centimeter, and the top and bottom cost 2 cents per square centimeter. We're going to find the dimensions that minimize the total cost of materials. So let's really think about what we are doing here. So once again, we know that volume of a box is going to be equal to length times width times height, which we're told is 512 cubic centimeters. Okay, so we're at 512 cubic centimeters. And let's once again just solve for height. So height is going to be 512 over LW. And for this, you can once again solve for W, solve for H, whatever you want. But we have to make it simplify into a 2-variable function is our goal here. And so now we have to figure out a function for the cost. So the cost is going to be dependent on the surface area times the price per area of material. So cost is going to be equal to, so 0.01, so 1 cent times 2 L times H, so this is the top and bottom, or sorry, this is the sides, L times H are the sides, plus .01, so still looking at the sides, times 2WH, okay, so 2LH, 2WH, they're each a cent each, plus 0.02, 2 cents for the top and bottom, and that's going to be 2 LW. Okay, so let's just simplify this a bit. So the cost is going to be 0.02 LH plus 0.02 WH plus 0.04 LW. Okay, so now we need to plug in H equals 512 over LW. So C is going to be 0.02 L times 512 over LW plus 0.02 W times 512 over LW plus 0.04 LW. Okay, so the cost is going to be 0.02 sorry. This is the last exercise. Hang in there. So, got ahead of myself, actually behind myself, looking at these notes. Okay, so C is going to equal, when we multiply this out, 10.24 over W plus 10.24 over L plus 0.04 LW. All right, so there's our function of cost with respect to width and length. So now what we can do is we need to figure out where the gradient is 0. So let's keep going. Okay. So let me just write this down one more time so that we have it. Okay, 10.24 W to the minus 1 plus 10.24 L to the minus 1 plus 0.04 L times W. So we need to take the partial derivative of cost with respect to W. Okay, and so this is going to be minus 10.24 W to the minus 2 plus 0.04 L. Okay, and we can do the same thing with respect to L. Minus 10.24 L to the minus 2 plus 0.04 W. Okay, and so now we need to find the critical point. So, setting this CW, say, to 0, you end up with 0.04 L is equal to 10.24 over W squared. And similarly, for the other one, you end up with 0.04 W is equal to 10.24 over L squared. So clearly, W is going to equal L in this case. So W is going to equal L is going to be 6.3496 centimeters. Okay, and that means height is going to be 12.6992 centimeters. Okay, we have the dimensions. But let's just verify right? In fact, that we have a min. So, add one more page. Okay, so I'm just going to give us CWW. It's going to be 20.48 W to the minus 3. CLL is going to be 20.48 L to the minus 3. And CLW is going to be 0.04. So if you compute D at 6.3496 and 6.3496, we end up with 0.0048, which is greater than 0, of course, and so we have a min. Well, because CWW is greater than 0 right here. All right. Well, thanks for sticking with me for this one, and I will see you next time. See you then.